All right. Looks like we got our editor open. We got Chrome open with the advent of code. We've got our coffee. So now we're ready to do day 19. Today's problem is called beacon scanner. Let me get the window a little bit wider here. I guess it doesn't really matter. Whoops, how did that happen? Let's bring that back up. Okay. As your probe drifted down through this area, it released an assortment of beacons and scanners into the water. It's difficult to navigate in the pitch-black open waters of the ocean trench, but if you can build a map of the trench using data from the scanners, you should be able to safely reach the bottom. The beacons and scanners float motionless in the water. They're designed to maintain the same position for long periods of time. Each scanner is capable of detecting all beacons in a large cube centered on the scanner. Beacons that are at most 1,000 units away from the scanner, in each of the three axes, X, Y, and Z, have their precise position determined relative to the scanner. However, scanners cannot detect other scanners. The submarine has automatically summarized the relative positions of beacons detected by each scanner, your puzzle input. For example, if a scanner is at XYZ coordinates 500, 0, negative 500, then there are beacons at negative 500, 1000, negative 1500, and 1501, 0, minus 500. The scanner could report that the first beacon is at negative 1000, 1000, negative 1000 position relative to the scanner, but would not detect the second beacon at all. Unfortunately, while each scanner can report the positions of all detected beacons relative to itself, the scanners do not know their own position. You'll need to determine the positions of the beacons and scanners yourself. The scanners and beacons map a single contiguous 3D region. This region can be reconstructed by finding pairs of scanners that have overlapping detection regions, such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely determine where the scanners are relative to each other, allowing you to reconstruct the beacon map one scanner at a time. For a moment, consider only two dimensions. Suppose you have the following scanner reports. Okay, I guess these are just relative positions of beacons. Drawing X increasing rightward, Y increasing upward, scanners as S and beacons as B. Scanner 0 detects this. Okay. Scanner 1 detects this. All right. For this example, assume scanners only need 3 overlapping beacons. Then the beacons visible to both scanners overlap to produce the following complete map. Unfortunately, there's a second problem. The scanners don't also know their rotation or facing direction. Due to magnetic alignment, each scanner is rotated some integer number of 90-degree turns around all of the X, Y, and Z axes. That is, one scanner might call a direction positive X, while another scanner might call that direction negative Y. Or two scanners might agree on which direction is positive X, but one scanner might be upside down from the perspective of the other scanner. In total, each scanner could be in any of the 24 different orientations, facing positive or negative X, Y, or Z, and considering any 4 directions up from that facing. For example, here's an arrangement of beacons as seen from a scanner in the same position but in different orientations. Okay. By finding pairs of scanners that both see at least 12 of the same beacons, you can assemble the entire map. For example, considering the following report. All right. Got 4 scanners there with lots of beacons that they see. Because all coordinates are relative, in this example, all absolute positions will be expressed relative to scanner 0, using the orientation of scanner 0 and as if scanner 0 is at coordinate 0, 0, 0. Scanner 0 and 1 have overlapping detection cubes. The 12 beacons they both detect relative to scanner 0 are the following coordinates. These same 12 beacons in the same order, but from the perspective of scanner 1 are these. Because of this, scanner 1 must be at 68, negative 1246, negative 43 relative to scanner 0. Okay. Moving on ahead. Fullest of beacons relative to scanner 0 is this thing. Okay. In total, there are 79 beacons. Assume the full map of beacons. How many beacons are there? So yesterday we felt like the difficulty of the advent of code problems stepped up tremendously, and today's seems pretty gnarly as well. I remember a problem that was similar to this one. I want to say a couple years ago, where I didn't end up getting the correct answer after spending like 4 or 5 hours on it, and then I looked at the solutions that other people uh, posted, and I don't think that they were actually correct. I wonder if I can find that particular example going back in time. I want to say it was the one that I did in OCaml, but I'm not 100% sure. It will take me a while to actually figure out where this one's located. So maybe it's not going to be an easy one for me to find. Gosh, I'll just click around and see if there's anything in here that. No, this one was like simulating a computer. Well, you know what? I'll probably look for that later on and see if this is similar. Hopefully, we're not in the same situation where it's kind of like a problem that's actually difficult to determine the actual answer for. Anyways, let's take a look at the input. So we've got scanners and we've got the beacon positions that they're all picking up. So the interesting curveball that they've added to this problem is that the scanners can all have different orientations. If they didn't have different orientations, it would be relatively easy to find the overlapping beacons between the scanners. And the reason for that is that we could just find, essentially, if these are all relative positions, we can essentially just find, we could determine beacon positions relative to each other. And if orientation isn't a concern, we could basically find sets of beacons who have a certain relative orientation to each other, or a certain average position, and then just compare those sets between the different scanners. For what we have to do this time in the actual problem, I think we actually have to also perform potential rotations around axes to determine if we find those patterns. I think both of those are actually a little bit tricky. So it would be enough for us to even figure out the first problem, like what if there was no orientation difference between the scanners? Can we find the overlapping beacons, or the beacons that they share? They mentioned in here the notion of 12 beacons, and I don't know what the significance of that is. I'm trying to see here. Scanner 0 and 1 have overlapping detection cubes. The 12 beacons they both detect relative to scanner 0 are at the following coordinates. So what I'm trying to figure out here is whether this number 12 is actually like the number you have to know in order to like figure out the relative position of two scanners, or if it is more that the region can be reconstructed by finding pairs of scanners that have overlapping detection regions such that there are at least 12 beacons that both scanners detect within the overlap. By establishing 12 common beacons, you can precisely... So they're trying to say that, like, maybe if you find the 12... Is it 12 beacons that all of the scanners overlap with each other? That's a little bit unclear to me in this problem definition. Or is it that we're guaranteed that at least 12 beacons are shared between each scanner's pairwise relationship? Maybe that's what it feels like they're trying to say. At the very least, let's just try to read in the input. I'm not sure if the scanner names really matter. We just need to know what the 0th one is. I guess a scanner will be represented by a vector of a 3-tuple XYZ coordinates. I'm going to go ahead and make an XYZ struct. I know we could use a tuple, but I think I like the idea of using a struct just so I can type the letters X, Y, and Z. It'll be a little bit easy for me to think about. So it's a vector of points. Each scanner is a vector of points. And then the points are in relative space. So the X, Y, and Z coordinates are relative to the space that each scanner defines. Maybe what I'd like to do is I'm going to do the trick where I keep an iterator so I can advance past these blank lines and these lines that have the triple hyphens on them. We're going to grab the next thing out of the iterator. If it's a new line, the line length is empty. We're just going to go to the next line. And then if the line how do I want to do this? The first thing we're going to expect is actually a triple hyphen thing, right? And then I want to accumulate this interior vector and then push that interior vector onto the outer vector, right? So maybe do I want to be able to peek at this thing? Why don't we say that our iteration, the inner loop of this iteration, is going to be essentially over this chunk of data, which also includes the new line between these. And then we have to special case the very last item in this list, because it might not have a new line at the end. So let's just loop. And what we're going to do is we're going to assume that what we're reading in at the top of this loop is one of these hyphens. Okay. And so we're just going to do lines.next. We're going to have a list of scanners. we're going to create the points, a vector for points in this particular scanner. And then what we're going to do is we are going to consume off of the iterator lines until we either hit a blank line or the end, right? So if lines.peak is none, that means we've hit the end. And we need to break out of this outer loop. If the line starts with hyphens, we are done with consuming this particular scanner. Otherwise, we need to actually parse the point. So the coordinates equals line. We're going to split the line along commas. And we're going to map these tokens. We're going to parse these into a vector of I32s. So our point is going to be coming from these coordinates. And then at the very end, we're going to push the points, which is the list of points for a single scanner, onto the big list of scanners. Let's go ahead and print this out and see if we did it right. That feels like a little bit like an infinite loop, right? And I think what's happening is because we're only peaking here, we're not actually consuming the iterator. So we need to consume it right here. So I think it's complaining that I can't mutate lines because I'm borrowing it on line 21. What if I stored it in a temporary. Still going to complain. That's because this line option is still I think maintaining a borrow on lines. Okay. Well, the only reason why I think I need to do this match is because I'm just trying to check for this break here. So let's try this. If lines.peak is none, then we break the outer loop because we're done. Otherwise, we're going to grab the line. And just unwrap it. It's a little bit of an ugly pattern, but then we can just do the rest of this stuff here. We'll lose it. We'll lose a layer of indentation, which is always nice. And really, we can just start with a single hyphen. I think that's what we can look for here. Okay. Scanner's exclamation point. What is it actually complaining about here? Did I miss a closing brace somewhere? I am missing a closing brace somewhere, maybe because I added an extra. I think I deleted one already. I'm not sure which one I needed to add there, but it looks like it's compiling now. So now let's try running it again. Calling unwrap on line 32. Oh, it's because I added this next here. Whoops. Is it the line 30 unwrap? Yeah. It's complaining that I'm not able to do, I'm not able to split one of these. I'm not able to parse these into a I-32, which is interesting. I think what I want to do here is if it's none, we're going to break the outer loop. If lines we're going to peek again. All right, so maybe I'm going to bring that match back. We're going to match on the peak. This is me kind of like struggling with Rust a little bit. If it's none, we are going to break the outer loop. If it's a line, and the line is equal, the line starts with a hyphen, we are going to break the inner loop. Otherwise, we do nothing. They're calling this unreachable code, but it's not unreachable. This is a little bit confusing to me because this if statement really should be preventing maybe it's not interpreting this match correctly. Oh, it's saying that it's non-exhaustive. So I think what we want to do is just have an arm here that does nothing. Okay, let's try that. Still not taking. Let's print out every line that we're seeing. And we just want to make sure that we're not seeing anything that is not parsable. Okay, so there is an empty line. I think what I need to do is I need to actually consume the empty line. So if the line dot length is equal to 0, we're done. We're going to break here as well. Which actually means that this case is never going to happen. All right, so let's try if lines dot peak dot is none break outer. This is going to be a lot cleaner, and I think this will work this time around. All right, that's pretty satisfying. Okay, so let's take a look at the very last one. 0.676, 838. Negative 365. Looks like our last one is actually, we're actually not able to parse the final one for some reason. I think it's because when we get here, if we get here, we need to actually push this, we need to actually repeat this push here. So I think what I'm going to try to do is maybe change this pattern a little bit. I'm just going to say while lines peak is something, we're going to get rid of this branch or loop label, which is always a nice thing to get rid of. This is a little bit awkward. I don't like the fact that I'm kind of peaking twice here, but I think this is just the nature of this particular input. Okay, so that looks a little bit healthier. The last point that we were able to parse is negative 813, negative 584, and 814. Okay, so we've gotten past the parsing part, which is, I think, by far the easiest part of this problem. We need to come up with a way of figuring out what, given two different scanners, what orientation do they have relative to each other, and based on that orientation, what is their offset from each other? Let's assume that all the orientations are the same, right? And then the only thing that's different is like they have different relative offsets. What we can do what we're trying to do is intuitively find a shape that looks like this given those particular offsets, and then find a similar shape. I don't know if I can select this. Find a similar shape, this kind of triangular shape of B's, in another list, and that shape is going to be independent of where that scanner actually is in the 3D field. Now, to do that mathematically, I think we still need to pick like a particular relative position, right? So what we could do potentially is pick a particular beacon. Again, this is assuming that the scanner is oriented the same as the other scanners. We could pick a particular beacon in each list, and then adjust all the offsets within each of those lists relative to that particular beacon. And we would try every pair. So we would try using the first beacon in the first scanner's list and the first beacon in the second scanner's list, and use that as the origin. Update all of the offsets to make them all relative to that origin, and see if we get at least 12 similar sets of offsets. And if so, we've found the overlap And once we know the overlap, we should be able to identify the beacon that they have in common with each other, or at least one of those beacons that they have in common with each other. We go back to their actual absolute positions, right? And then, or rather, not their absolute positions. We go back to the position of the beacon relative to the scanner, and then that'll allow us to compare those two relative positions and get a relative positions between the two scanners. It's a little bit brute force, but we can try it. I'm going to work with these two scanners because we know that they are the same orientation to each other. So we will do a pairwise iteration over the scanners. And then we're going to basically pick a beacon within each list. To serve as a new origin. And then here, let's go ahead and create a list of points that are relative, as if they're relative to the A origin, right? So let A adjusted is equal to scanner A map and collect. We could actually even make this a hash set of points. We just need to be able to hash these things. So I think we can derive those pretty easily. So it's partial equal and a hash. We're just going to subtract off the origin's coordinates. And then from there, we're going to collect them into a hash set. Oops, I need to make this an iterator. We need to import hash set. These should be borrows. Okay, now that we've got A adjusted, we can create a B adjusted. Maybe these should be in function somewhere. Transform points, we will get a source of a vector of points, and we will get a new origin in their same space. And we will return a hash set of new points. And we can pass the point by value. It's not a big deal. So this transformation is exactly what I wrote in this code here. So let's call it let a x form transformed equals transform points of scanner A and A origin. And we'll do the same thing to get the transforms points for B x form. Our source this time will be scanner B, and our origin this time will be origin. And what we're trying to do here is now we're just trying to see if they have at least 12 points in common here. We're going to intersect with BX form. And we are going to count them. We have, if we do this, we found the we found the matching transformation. Or we found essentially what the actual intersection is. So maybe we should materialize the transformation. Okay, here's another thing. Is like, does the fact that we have lost the ordering because we put them into sets here give us some information less? Like, can we go back and know exactly which points we're talking about here? I'm going to go ahead and put the minimum overlap into a variable here. I have a feeling that this may matter. So if they overlap, what we're really trying to do here is determine we're basically saying that using this origin for the set of points A and using this origin for the set of points B causes them to intersect perfectly. Now, if we want to basically get points B in the space of scanner A, I think we take A origin and then we add B origin. Let me see if there's an example here. That gives us 12. Scanner 0 and 1 have overlapping detection cubes. Are they oriented the same way, though? Yeah, I don't know if Scanner 0 and Scanner 1 are oriented the same way. We could use this example, which is the one we've already copied, and let's just let the minimum overlap be 3. Let's here just print out A origin and B origin. And we can work from there. Oh, I am working with only 2 dimensions here in this example. Looks like we never get to this point here. Oh, we do. We get to this point multiple times. So A origin in here, gosh, I'm having a problem with window management here. A origin is 0, 2, 0. So we're talking about this point here. B origin is 0, 2, 0, which doesn't make sense because 0, 2, 0 is not a point in this second scanner. So I must have used the wrong variable name somewhere in this code. Because B origin is coming from scanner B. Scanner B should be a totally different scanner than scanner A, right? Oh, you know what it is? I want to start with A plus 1 here. Okay, this should be a little bit more clear. 0, 2, 0, negative 5, 0. If those are the same, does that imply then that 0, 2, 0, or 0, 2 and negative 5, 0 are the same point? Right? So 0, 2 is this point. 0, negative 5 is this point. Yes. So this, we're basically saying that A origin and B origin are the same point. I don't know if that's generically true. But let's go ahead and ride that assumption for now. If A origin and B origin are the same, if we can make that assumption that they are the same point, then the offset between the space that scanner B defines to the space that scanner A defines is going to be what? Is it B origin minus A origin? B origin minus A origin is negative 5 minus 0, which is negative 5. And 0 minus 2, which is negative 2. So that is how you get from a point in scanner 0 space to a point in scanner 1 space. But I actually want to go from a point in scanner 1 space to a point in scanner 0 space. So I'd subtract the other direction. So it would be A origin minus B origin, which is plus 5 plus 2. So if we add 5 to this point here, we'd get 0 for the x coordinate, and then we add 2 to the y coordinate, we get 2, which would map this coordinate to this one. If we did the same with minus 1, we'd add 5 here, which gives us 4, and then we'd add 2 here to minus 1, which would give us 1, which gives us the 4, 1 point. And then for this point down here, if we added 5 to negative 2, we'd get positive 3, and if we added 2 to 1, we get positive 3 as well. Okay, so let B to A is equal to essentially A origin minus B origin. Now, we don't have this arithmetic definition, like these arithmetic operations set up, but it might be worth doing it. So we're going to implement add for point. And that'll just be a point whose x coordinate is self.x plus rhs.x. Y is self.y plus rhs.y. And z is self.z plus rhs.z. We need to define an output type. And I guess this is output. So we need to do a subtraction as well, right? Okay, so where are we doing addition? I think we're doing addition in transform points. And A origin, I think we just need to dereference these. All right, so I don't know if I was doing much with B to A here, but this will at least tell us the offset from scanner B to scanner A, assuming that they have the same orientation. What we're really trying to accumulate here is just all of the unique points. Is that right? So what we could do at this point, let's create a hash set of points we'll call them beacons, and these are beacons points in scanner 0's space. It's a new hash set. And what we will do here is we will iterate over all of the points in the first space, all the points in the second space, and apply their relative transforms. What's tricky here is I don't know if scanner A is always going to be scanner 0, right? That's not always going to be the case. Maybe I need a table of transformations that will map a particular scanner into scanner 0 space. It'll be a hash map. And the first transform that we're going to have let's go ahead and create a transform here. We'll have a rotation, which I need to define somehow. And we'll have a translation, which is a point. We could even rename point to vector. We call it vec3 in honor of unity. And how are we going to define a transform? It could be the number of right-hand rotations around a particular axis in order. The problem with that representation is that it's not unique. But to enumerate all the unique rotations, I believe they said that there was like 24 of them, right? They're any one of 24 different orientations. Facing positive or negative y, x, y, or z, and considering any of the 4 directions of up from that facing. So how do we come up with a representation of rotations that is unique? It has 24 exact possibilities. And it's not so much that it's an absolute rotation that we care about, it's really more of like a transition from one facing to another facing. We'd also want to know how to do the opposite of that transformation as well. If we did do it in terms of rotations around the x-axis, and y-axis. The only problem, x-axis, y-axis, and z-axis, the only problem there, we know how to reverse that easily because we can just, if we do like n rotations around the x-axis, if we do a rotations around the x-axis, b rotations around the y-axis, and c rotations around the z-axis, the way to reverse that is we do negative c rotations around the z-axis, negative b rotations around the y-axis, and then negative a rotations around the x-axis. And that, but the problem is that is like, that's reversible, but it is infinite, right? We want to be able to try out a finite number of rotations. I mean, it's infinite, but at the same time, I mean, there are basically like, we could just put it into like 3 nested for loops, right? 4 rotations around the x-axis, 4 rotations around the y-axis, and then 4 rotations around the z-axis. So we could just call it a vec3 here. And then to rotate a vector, rotating around the x-axis means that you are changing the y component and the z component. One rotation around the x-axis, right? For using a right-handed system is going to take the first rotation is going to take the y value and move it to take the y value and then move it to the negative z value. Is that right? Or it'll take the y value to the positive z value. The second rotation will take, and it'll take a z value to the negative y. Self dot let priv z equals self let res dot z. Res z equals res dot y. And res dot y is equal to the negative priv z. So that's rotation around the x-axis. Let's call this axis rotations. A rotation around the y-axis is going to turn x into negative z. And it's going to turn the x into the previous z value with no sign change. I'm just imagining a 3D coordinate space. And what happens if you do a right-hand rotation around the y-axis? Your positive x is going to basically get swung over to into the negative z direction, right? So we're taking the positive x, reversing the sign, and assigning it to the z. And then the negative z is going to get swung over to the negative x direction, so there's no sign change. So that's what's happening here. And then finally, we want to do a z rotation. And under a z rotation, positive x is going to go to positive y, and positive y is going to negative x. So positive x is going to positive y, and then y is going to negative x. Okay. Maybe let's actually test this out a little bit. And I guess the question I have is if one way we could basically do all of our rotations is we can basically go from 0 to 3 inclusive across all three axes. And there's going to be some redundancy because again, like a vector 3 that describes a number of rotations is not going to be uniquely describing a rotation. So just getting an example, like we could have an axis rotation value of 1, 3, 1, and that may be equal to the same thing as like 2, 1, 1 or something like that. Those numbers aren't precise, but that's the problem with Euler angles, is that they're like, you can describe the same rotation using a Euler angle coordinate that has two sets of Euler angle coordinates that have two completely different individual values for those properties, which is okay. So if we wanted to transform, what we would do is we'd first rotate. And then we would add let's spell it out. Let's call it transform. Let's make an inverse rotation. And what this inverse rotation is, it's going to be this, but in reverse. I'm going to see if we can go without doing this inverse for now. Let's add it when we need it. And let's also add this when we need it. Let's see. Transform points. Where are we actually using this? How do we do negation? Is it neg? I bet this has a type output. I'm being very quiet because I'm not quite sure if I know what I'm doing here. So this transform here will actually be our axis rotations will just be 0. We're not changing anything. And our translation will be negative a origin. And rather than write a separate definition for the reference version, I'm just going to dereference here. This is a little bit of extra code, but I think it'll be worth it. Okay, I'd like to see if this ends up being our correct way of handling things. Okay, we're not collecting transforms just yet. Beacons, it's probably complaining because we're not doing anything with that yet. That's fine. All right, all of these additions, rotations, etc. needs to be declared as mutable. Let's see here. Xform, let's make it clone and copy. Same as a vector. All right, I'm going to try running that. After all that effort, looks like we don't get down here anymore. Zero, 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 4 minus 0, 0, 2, 1 minus 2 is -1. 3 minus 0 is 3, and then 3 minus 2 is 1. Okay, that transformation worked correctly. Ah, this is the issue. I copied and pasted. Okay, cool. So we found this 3 times, which is great. And basically the mapping from a point in space B to a point in space A is 0 to 5. And in fact, we can also do a rotation for all of these. This is, again, I think more than we need. The B to A transformation is going to be a new X form whose axis rotations is equal to this. In fact, let's actually just call this variable axis rotations. Yeah, these are going to be non-unique, but that's what we knew was going to happen. Yeah, see, a rotation of like 4 rotations around the z-axis just brings you back to the beginning. And apparently 2 rotations around the x-axis, 2 rotations around the y-axis, and 2 rotations around the z-axis also brings you back to the beginning. It's a little weird that we got back to 0, 0, 0 again. But I think that's because we're also trying different origins here. Okay. Now that we've got that as a basis, I think this is a decent foundation. Now we want to actually change our iteration. We're not going to do pairwise. We're not going to do pairwise comparisons between every single set. We're going to start with what we know and then build up from that. So what we do know, our transforms are going to be a hash map. And they're going to start with a transform for scanner 0, and the transform value is going to be no rotation, and the translation value is also going to be no translation. And what this is saying is that to transform a point in scanner 0 space to a point in scanner 0 space, you basically apply no transformation here. Oh, what I want is 0. And we're probably going to have to give this hash map a type, or else Rust is not going to really know what we want to do here. This is a U size mapping to an X form. It's going to be okay if I get rid, and then why is it complaining about the type here? And with an add, okay, it's probably insert then. And if I got rid of this here, is it still going to play ball? Okay, great. Okay, it thinks it's an I32, but we're going to use that value as a U size eventually. Okay. So then we have our list of unknowns, right? And this is going to be a hash set into which we're going to insert every other scanner's index. And while our list of transforms is not the same size as the list of scanners, because eventually we want to have a transform for every single scanner. What we're going to do is iterate over all of our known transforms move them into scanner 0 space, and compare them with each one of the unknowns. And if we find an overlap, we create a new transform for that scanner, remove it from the list of unknowns, and add it to the list of knowns. Actually, this outer loop, really we want to just do this with the most recent thing that we've added. But I think we're fine just doing it the way we're doing it right now. So we are going to say for... I don't think we care about the original scanner index, but we do care about its transform in X forms that we know about. maybe we do actually, scanner ID. Let scanner points equal to scanners of the scanner ID. And then we want to transform those into the space for scanner 0. Great. And now what we're going to do is we're going to say for unknown ID in the unknowns.iter, and now we're going to basically try every rotation, every so for each one of the points, okay, so for each rotation, we're going to go ahead and rotate the unknown points. Transform points of scanners unknown ID, and our transform is going to be axis rotations, which is a vec3 of x is x rot, y is y rot, z rot. I think I could have copied and pasted this. And our translation in this case is going to be nothing. So now what we've done is we've taken the unknown points and rotated them into a particular rotation relative to their own space. So actually we do need to do the inverse rotation, I think. Okay, so we've done the rotation. And so now that we've gotten our points rotated, we can do our original crazy thing here. Basically picking an arbitrary origin in the first space, an arbitrary origin in the second space, and comparing the two. So we can do for A origin in scanner points. Let B origin, and then in here what we're doing is we're creating a transform. What do we need AX form for in the first place? Are we using it for anything? Oh, it's a hash set. So I could translate points that just we're going to do P plus translate. You can dereference. Okay. And then maybe I'll do a rotation and an inverse rotation. So this can become rotate points, and our rotation ends up just looking like this. So clean up the code a little bit. We are translating by is negative a origin. The source is scanner points. We're just picking an arbitrary origin to line up. Found reference to hash set. I guess I can make scanner points a hash set. I think what that means is this needs to be a hash. This points needs to be a hash set. And instead we insert this. There's probably some other places we needed to worry about here. Transform points. We'll call this a hash set. We'll call this a hash set. Doesn't really matter. We know that they're all unique. I don't think the ordering between them really matters. All right, we fought through the type checker, and now we want to pick a pivot for the coordinates in the unknown set. Be transformed equal to transform points, actually translate points. And this is going to be unknown points. And the translation is going to be the negation of B origin. And then we are going to repeat this intersection here. Gosh, this code is ugly. Don't feel great about it. So if A transformed and B transformed, if the intersection between them is greater than or equal to the minimum overlap, which in this case is going to grow to 12, then we're basically able to figure out what our translation is going to be. Now, the issue here is that the transform here, what we want to do is to take something in... Actually, I think it's just going to be X rot, Y rot, B rotation here. And the reason is we want to take something in space B and move it into space A. And that's exactly what these rotations are doing. These rotations are essentially lining space B to space A. So let's go ahead and stuff this into a variable. If I can get rid of that pop-up. Let axis rotations equal to this. Too many pop-ups. I'm getting confused. The IDE is getting confused. All right, so once we've gotten here, we have found our rotation that we want. So what we can actually do at this point is insert. We can say vector, what is it? Our x forms, insert, and which transform are we on? Is it unknown ID? And we'll insert this transform here. Probably gonna have to dereference here. Consider dereferencing the borrow asterisk. Okay, so now the problem is xforms is we are trying to insert into it while we are looping over it, right here. Okay, so why don't we collect this into something that we can iterate over? And let us call this a vector of u size, a tuple of u size and an x form. How do I map these into dereferenced? I mean, I can do something really ugly, which is this. Or what it actually is a b into star a star b. We should do a copy. Gosh, that is hideous. And now that we've cloned these, we don't need all of these extra dereferences, which makes that a little bit cleaner. and we can modify X forms. But now we need to know where to break. And in fact, not only have we found X forms here, we've actually, unknown is now known. So we can just say that unknowns is, we can remove unknown ID. And this is going to complain because I'm trying to mutate a borrowed value, right? So I think we need to do the same thing here. So we can say like, let current unknowns as a vector of u sizes is equal to unknowns dot iter, or we can actually clone this, right? Or it's a hash set. Fine. And this can be current unknowns. Can get rid of this dereference. We need to dereference this. And now we need to know like where we're actually breaking out of. We have now modified both X forms and unknowns. So we actually need to break out of, this thing, or we need to continue this thing. So once we get in here, we've modified X forms and unknowns. So we need to go to the outside here and check the condition again, and then go from there. And then, okay, all this code down here that I wrote before is no longer relevant. I can get rid of it all. Boy, this is a nasty, nasty function. But what it's really just doing is it's saying, okay, I'm starting with basically scanner 0 and all those beacons as points that I know are already oriented and translated to the space that I want them to be, right? And then from there, what I'm going to do is I'm going to say I want to compare that against every other scanner, okay? And for that other scanner, I'm going to rotate it a bunch of different ways. And one of those rotations, hopefully, will allow me to kind of like translate both the stuff that I have in scanner 0 space and the stuff that I have in the other scanner space. We're going to kind of do this sort of like relative comparison, so we can basically compare these shapes that we're seeing here. And if those shapes resemble each other, then we basically have found the appropriate transformation, both in terms of the rotation that we need to do first and in the translation. And that takes that other scanner from a scanner that we didn't know anything about before to one where we now know its relative orientation and position relative to the space of scanner 0. So we're going to say, okay, we're going to store that translation and then remove it from our unknowns. And now that we've updated both of those, we should have one more transform that we know about, one less unknown that we know about. And we're going to go back up and then try again. Now, the wrinkle in this problem is I don't think every single scanner has points that are relative to... we can't just compare scanner 0 against every other scanner set and find 12 overlapping points in this search process. So we actually need to try everything in our set of scanners that we have, that we know about and that we know how to translate back into the space of scanner 0. We're going to try each one of those that we know about against each one of the ones that we don't know about. And that's what this loop here on 151 is. Okay, so this is pretty nasty, but once we've done that, I think what we can do now, and really we can do this inner loop if we wanted to, but what we can do now is we can create a beacons hash set. And we can loop over all of our transforms. We don't care about the scanner ID anymore. Or we do, actually. Scanner ID, transform, in our list of transforms, which now should have one transform for every single scanner. We are going to for every point in scanner's scanner ID, we are going to insert p.transform of using the X form for that scanner. Let's just make this an iterator, which is fine. And then what we can do is we can print the number of items here, which is what we're looking for. Length. Okay. I'm just gonna run it over our input and see if it even terminates. I'm kind of thinking that the probability of there being a bug here is pretty high. Oh, and we need to adjust our min overlap here to 12, or else it's not going to give us what we want. This feels like an infinite loop. So what an infinite loop implies is that by the time that we get down to the end of this loop here, we have not been able to add something to our transforms and remove something from our unknowns. So let's actually even call this unreachable code, right? We should never get to this point. And I think we're going to hit that. So if we don't hit that, similarly, we should never reach the bottom of this loop. Well, that's not true. We just don't want to ever reach the bottom of this loop here. So this is the unreachable one. Now, it could just be that we're just doing so many rotations in the search, but this isn't that many, right? This is like 4 times 4 times 4. It's just, we're just basically running these internal things 12 times. And then each list of these has 30 of these. So 30 times 30 is like 900 times 12. You know, we're basically talking about like 12,000 or 24,000 or 25,000 iterations. To find a new one. It doesn't seem like this should be taking as long as it should be. So I think we need to figure out where we are infinite looping. So we could just go into one of our inner loops here. And the most interior loop is this one right here. And we can just print out what's going on here. It is A is our scanner ID, B is our unknown ID, our rotations, and our A origin, and our B origin is here. And then we're just going to go ahead and plug all this stuff in. So we've got an unknown ID or a scanner ID, unknown ID, axis rotations, A origin, B origin. And for our vectors that we're printing out, we're going to want to debug print these. And let's actually add an extra new line at the end here. Maybe what we can do is stick this println a level higher. And maybe what we just want to know is what our unknown and known is. Let's start like that. And is this seeming to get smaller and smaller? Yeah, so the search maybe for each one of these is quite slow. And then maybe down here we can actually just print what we found, right? And hopefully we at least print something out for that. Let me try the release build real quick, just to make sure that this is... It's considerably faster. Okay, discovered a transform for 22. Okay, so we got to a point where we were not able to reduce the list down. So at this point, let's try running it against the sample input. And in fact, is there... Let's do scanner with 0 and scanner 1 here. Transform for 1, transform for 3. And then we're getting down to here where we're not able to find anything. That is a little tricky, isn't it? We're going over known transforms, and then we are going over the current set of unknowns. We should always be able to find an overlap. Zero and 1 have overlapping detection cubes, which means that we found the one for 1 there, right? Scanner 4 overlaps with scanner 1. And they don't talk about what scanner 2 and scanner 3 would overlap with. They're saying that scanner 3 overlaps with scanner 1. Tricky. There is an optimization that we can add to make this a little bit faster, where we know if we have tried comparing one scanner to another scanner, we can stick it into a blacklist and avoid that combination again when we do this loop. So what I mean by that is if we get to a point down here, don't overlap, add to deny list so we don't try again. So let's try that. Let mute deny list equals hash set new. We're going to insert down here. And then up here, we're going to say if deny list dot contains scanner ID, unknown ID, then we continue. And that should work a little bit faster. Probably not that much though. Yeah. So we discovered the transform for 3. And where am I sticking the unreachable? It's right there. It's almost as if this unreachable is not happening at the right time. Or this continue is not doing the right thing that I want. Continue outer should just jump out to over here. So let me just println starting new outer loop. We're going for 3, 0. So we're starting a new outer loop, but for some reason the outer loop is not trying transform 1 because like 1 should have gotten inserted here, right? We discovered transform for unknown ID here, which means that X forms should have a key for transform 1, which means that when we loop over known X forms, let's call this known ID. Let's call this known points. And I think we can just save ourselves a line of code like that. Known ID, so basically transform 1 should pop up again as a known ID. It's really weird that that's not coming up. Let's go ahead and print what xforms contains. Starting out our loop, we have an X form for 0, we have an X form for 3, we have an X form for 1. Okay, 1 is in there, and yet somehow we are breaking out early. Unless our deny list is what is preventing this from happening. Let's print this above the deny list. Check. Yeah, there we go. So we are doing 1. This says 1 and 4 don't have an overlap here because it didn't discover an overlap. But according to this, it says scanner 4 overlaps with scanner 1. I kind of want to see what this is. Unknown ID equals 4. I just want you to print this every time we attempt an intersection. And I want to know how high this number ever gets. It only ever gets to 1. So I wonder if there's something funky going on with our rotation logic in particular. That's the one that I have the least confidence in. So I guess I can try to narrate out loud what we're doing again. We have an outer loop that says, okay, we want to find a transform for every single scanner that will map the beacons within a scanner into the space of scanner 0. And the only one that we know at first is scanner 0's transform, which is going to be nothing, right? It's going to be this transformation. There's no rotation, there's no translation. So we start with scanners that we know the translation for. And for each one of those, we're going to compare them against scanners that we don't have the transformation for. And try to see if each one of those pairwise comparisons will yield 12 overlapping beacons if we take the scanner that we don't know, try a bunch of different rotations on it, right? And then see if we can do a similar shape comparison that we do here. And maybe we can even map these, we can even shove these into functions if it makes it a little bit easier to read, which maybe I will try. It's just some number, I32. So we are going to say let a origin, or let's just write this loop again. For a origin in a.iter, and what we're going to do is we're going to say translated is equal to translate points of A and minus A. And then we're going to say let B translated. Let's translate points. A translated, the intersection with B translated, length dot count is greater than or equal to min similar, then we return true. Let's call this a U size. And let's call this has similar shape. If has similar shape, we're going to say the known points, the unknown points, and min overlap. So what goes inside that if statement is this. And we may have a few extra brackets, maybe 3. Well, we kind of need to know the origin. So maybe what this is going to be is it's an option vec3, which is an offset. And this is going to be none here. And then here we're going to return sum. And we want to go from B to A. So we're going to do A origin minus B origin. I think we may need to dereference these. Oops. If let sum offset is equal to has similar shape, this is going to be the offset. Okay, so that's a little bit easier to read, I think. We could make a function that does all these rotations, right? That gets an iterator. Vec of vec3s. Let result equals a new vector. And then we're going to do result.push of vec3 with x is x root, y is y root, z is z root. And then we return the results. And we can replace this whole thing as for axis rotations in all rotations. That will let us trim off a couple of brackets here. Okay, this is starting to look a little bit healthier. It's not going to change the result here, unless it helps us find a bug. Looks like my language service is having an issue here. I'm going to reload the window. I still probably have a bug in here, but let's just start from fresh to see if it can do a little bit better job of telling us where the issue is. Waiting for these little spinners to finish up. We have so many directories in here now that it's starting to get a little bit slow. On the other hand, it's not all that much code, so it's a little bit disappointing that this isn't faster. Could be that I've got other stuff going on this computer. I don't really know. It's indexing the standard library. Boy, what the hell happened? I don't know what happened. It's almost as like a cache got cleared out by accident. That is chugging along. I'm almost tempted to just completely close the editor, but I feel like that might not change anything. Is my CPU getting eaten up? The CPU load is pretty high right now, but I mean, I'm running a thing. OBS is taking 4 CPU cores right now. That probably doesn't help. But everything else looks pretty calm, pretty chill. Nothing unusual. Boy, how long is this going to take? All right, I'm going to close VS Code and see if I can restart it. Hopefully I won't regret that. Okay, I'm going to just try running this. This will also tell me whether or not I've got any issues. Line 117 needs to be mutable, of course. Of course. Okay, so yeah, it didn't change the results of it didn't change our answer, but I think I made the code a little bit cleaner to look at least. Okay, so I was walking through all these. We're basically saying while we still have some unknown things left, and maybe what I actually should just do is, well, I'll just call this unknowns.length is greater than 0. We are going through the stuff that we know. We're starting with one of those. We're pulling out its known points and transforming them into the space. We're transforming them into scanner 0 space. Then we are going through all the ones that we don't know yet. And if we've already tried to compare one that we know and the one that we don't know, it's like going through it again is not going to help us. So we should just jump out of that. Then we just basically say for every single rotation that is possible, and again, this should be more than enough rotations. And I think we can account for every single orientation. Is that correct? These are 4 possibilities. These are 4 possibilities. These are 4 possibilities. 4 times 4 times 4 is 1664, right? 64 possibilities, of which, boy, there's supposed to only be 24 unique ones. So 40 of them are, 40 of them are not necessary. So that's probably where a lot of our slowness is coming from. We can sit there and try to reason about maybe which ones aren't necessary, but let's not worry about that for now. Okay, so for each one of those rotations, we are going to rotate all of the points in the scanner set that's unknown. And then now we have, for our known points, stuff in scanner 0 space. And for unknown points, we're hoping that we found an orientation that lines up with the scanner 0's orientation. It's just that the offset is off. So here we're searching rotations, and here we're going to search offsets, right? And maybe we can try to call this find offset, right? And inside finding the offset, we're basically picking pivots in each of the two sets that we're comparing. And if there is a similar shape between these two sets, basically that means some point in set A and some point in set B are actually the same. And we'll know they're the same if we translate all the points in each of their respective sets, and at least 12 of those, or whatever our kind of like minimum satisfying number, at least that number of them are going to have the exact same coordinates, which is what this intersection is giving us here. And then we're going to go ahead and return the offset of translating an element of set B into an element of set A. Find offset. Okay, and if we do find it, we'll have the offset. We'll go ahead and insert. We'll go ahead and remove unknowns. Let me just do that first. And then we'll insert that transform into our list using the rotation and offset. So the rotation here, one question I had is like, are we going backwards? Like, is this rotation here? It's the rotation that we want to apply to the points in the unknown set to get us into to align us with the rotation for scanner 0. And we're applying the rotations here to the unknown set. And then when we apply the offset, yeah, that should do it. Okay, well, here's actually an interesting thing. Is the offset that we're getting here. The offset will get us into I think this is maybe incorrect, where the offset here will get us from space B into space A, but it does not get us into space 0. So this is another bug that we haven't even run into yet. Like, what we're running into right now is we don't even get into this area. But the bug I'm saying is that, like, essentially this value is wrong. This offset goes from B to A. Let's call this B to A. And maybe what we can do is call this, like, find all, not find all references. That's not what I wanted to do. I wanted to rename this to AID. A points. BID, and let's call this B points. Okay, I think maybe that bug that I was talking about is not a concern anymore, because A points, we're actually translating. We're both rotating and translating these. So these should all be relative to scanner 0, all of these values. So if we find an offset between A and B here, then B to A is actually translating into the space for scanner 0. So I think we're okay there. Boy, this is super confusing, isn't it? So in order for us to actually test this out, I think we're beating around the bush here a little bit, because like what we really need to do is just make sure that we are correctly doing this search. And in order to do that, we need to have some actual data that will tell us this. So for example, we could do scanner 1 and scanner 4, because those we know should overlap. That's what it's saying here. Scanner 4 overlaps with scanner 1. And these are their overlaps relative to scanner 0. So one thing we can do is, it's telling us the 12 overlapping beacons between scanner 0 and scanner 1 of the sample input. And they're giving us the coordinates in terms of scanner 0. So why don't we go ahead and print them out, right? So if we do find offset, if we go into here, let's take the overlapping points. Oh, and we can't do the over. We need to actually translate them. And then what we're going to do is we are going to get the intersection between A points and the B offset points. And why don't we go ahead and just print these? Okay, so here we discovered a transform for this one, and I think this, you know what, let's reverse the order of these printlins, or else we're going to get super confused. This is all debugging code anyways. Okay. It's this one here. And this is without rotations. So if we got this right, then we know that our translation code is probably going to be correct. All right, so the 12 beacons that overlap, there's a negative 618, negative 824, and then the z is 0 here. So I think what's happening is our z is getting set to 0 somewhere. Did I forget to add a z value somewhere? Why is z coming out as 0? Let's look at our primitive math and see if we're missing a coordinate somewhere. Our addition is definitely adding the z value. Our subtraction is definitely subtracting the z value. Negation is definitely negating the z value. 0 is returning a value for z. Um, I remember at some point, maybe I was flattening. This is the issue. Because we were doing a 2D example. 79. Okay, so that was our bug, is we were basically using, we were using some leftover 2D code. Oops. Let's go ahead and maybe get rid of some debug printing and see if we can find something for our actual input. Oh, oops. I did not copy over the right file. We're still debug printing somewhere. Let's run it again. This should take considerably longer than the debug input. And it's because I'm doing so many rotations that I don't actually need. But I'm hopeful that we will eventually get there. The reason why I'm hesitant to reduce these is that I'm just not that smart, right? I don't know which of these rotations are redundant to each other. $430. Took a long time to number crunch. Crossing fingers. All right, we got the right answer. So our search is slow, but I think we were able to find an algorithm that is sort of brute force. Sometimes it's a good idea to appreciate just how big the ocean is. Using the Manhattan distance, how far apart do the scanners get? In the above example, scanners 2 and scanners 3 are the largest Manhattan distance apart. In total, they are this many units apart. What is the largest Manhattan distance between any two scanners? Okay, so we actually need to find the position of the scanners. We know their relative offsets from scanner 0 and their orientations. So we can just run that again. Boy, there's a lot of them. And then just compare them pairwise to each other to see which of the two have the largest distance between each other, right? So what we could do down here is, well, first of all, let's go ahead and just commit this code. And we can modify a copy of this to our heart's content. T19B. If I run this again, it'll compile, but it'll take forever to finish. So I'm not going to worry about that for right now. What I will do is reload the project just to make sure that Rust Analyzer can pick up this new directory. And here we are going to, rather than count the number of beacons, we're just going to collect the offsets from each other. Equals beacons xforms dot map, and we don't care about the key, we do care about the transform, and we're just gonna get the transform. We just want the translation. We're going to collect that into a vector. And then we're going to do for I in offsets in 0 to offsets dot length minus 1 for j in I to the offsets dot length. This is a pairwise comparison, and I think we're just going to do I plus 1 here. And then we're going to subtract j from I and get the absolute values. What are you complaining about here? I think the language service is just behind. Okay. Okay, so let distance equal to offsets j minus offsets I. It doesn't matter what order we subtract them. And we are going to add the absolute value of the x, y, and z coordinates. Best.maximum of d.x.absolute value plus d.y.absolute value plus d.z.absolute value. And then we're going to print out the best. So those are the Manhattan distances of the scanners relative to each other. Does it translate? Yes, translate. Okay, and if we run this, it'll just take forever, but it should work. And the first optimization I try to make is to see if I can reduce the list of these rotations down from 64 to 24. One way that I could imagine trying to reduce the redundancy might be to create a list of, like, just basically make a vector that points down the x-axis, for example. And what we will do is we'll basically push down a list of rotations and write into a hash set the final rotated value of the vector that was originally just pointing down the x-axis. And to remove the redundant ones, we'll keep that set and then just not push onto the vector if we end up with a vector that we've already seen, right? Or rotated vector that we've already seen, because we'll know that rotation is redundant. And we should come out with 24 unique rotations out of that. That's what's interesting though, is I think that might not be, that test might have some false positives. Because we need to worry about essentially the the rotation around the axis as well. So I guess that's not the best way of doing it. The other thing that we could do is just manually enumerate all 24 of these rotations and kind of try to work out in our heads what the translation of a vector would be, or how we should move the coordinates of a vector. But that seems like a pain in the butt, quite honestly. So I'm not going to worry about it for now. I'm just going to let this run for a long, long time. This loop down here should be really fast. So I don't think we're adding a significant amount of extra time over part 1 of today's problem. Got the last bit of my coffee. Chug it down for good luck. It totally feels like this is taking like way longer than the original one. And it's because I'm not running the release build, which I'm sure means that it's much, much slower. Yeah, if I didn't have this deny list early out, it would take probably longer than I'd be willing to wait. Other than that, I think the internal iteration for find offset here is necessary. Because we really have no way of knowing which pair of points within these sets are corresponding to the same point. That's essentially what we're doing here in this set, is in this double loop here, is we're just trying to find between these two sets which of these points is actually representing the same beacon. All right, 11,860. I don't want to wait that long again, so I'm hoping I got it. Okay, whew, we got it. All right, so the problem with this solution, I think after we've kind of like banged it out, it actually makes some amount of sense what we're doing. We're basically whittling down a list of unknowns, and we have to find a rotation for that unknown that might line up to another scanner that we already know. And then once we do that just by trying all the possible rotations. And so for each one of those rotations, we just assume that that's correct, and then try to find offsets between those two translated sets that will give us an overlap of 12 beacons. And I think the performance problem that we're talking about right now is really, this is taking, gosh, I don't know, like each iteration of this thing is taking about, 3 times as long as it should. So it's slow and it's not great. But we eventually came down to an answer fighting through it. I'm going to say that this particular problem, was it harder than yesterday's? I think yesterday's, once we came to the realization of what the actual trick was, it was not too bad. This one could have been way worse. I feel like we got lucky in that we wrote a lot of code. Like, I think this is enough code that it's kind of like there's 4 or 5 nested loops. We've got traits. We're writing our own little vector math implementation. Yes, I could have gotten a crate, but you know what? It would have taken me just as long to remember how to use cargo to grab that stuff as it did to actually make this. And I think our actual algorithm worked. We really just had to come up to realize that we added a bug when we were testing with 2-dimensional input. And maybe to avoid that mistake in the future, I should try to add a comment somewhere that just says a fix me. But then again, I'm not looking for fix me's, so I wouldn't have even known to look for that. I think I just had to basically try to print out my expected answer earlier, because once we compared the example output to the output that this program is producing, we found that bug really quickly. So probably need to go back to the examples a little bit more quickly. Other than that, I was in the middle of trying to assess whether I felt like this problem was harder than yesterday's, and I would say the answer is roughly yes, right? It's just more complicated. There's more cyclomatic complexity, to use the fancy word for it. It's just a more complicated program. It's an gnarlier program. All right, well, we're getting close to the end here. We've got day 20. We've got basically 6 more puzzles to go, and I feel like the last puzzle is always pretty trivial, right? I think, or it's just click a button. So we've probably got about 5 more days left of this. We've already hit a significant kind of increase in the amount of challenge, the amount of time that it takes to solve these. But that's okay. We've got some time to do it, and we're having fun. All right, we'll talk to everybody tomorrow, probably similar time.